All right, hi everyone, welcome back to chemistry. In this video, I'm hoping to do just a short video on trends in periodic properties. So these are trends that we see in elements that we can kind of predict using the periodic table. Okay, so the first thing I want to do is I want to define valence electrons. So valence electrons are the electrons that are in the outermost or highest energy level. So remember when we looked at silicon, we said that it had 4 electrons in its highest energy level, which it's in period 3, so that's going to be 3. So we said that it had 4 electrons in its highest energy level. So we could call those valence electrons. We could also say silicon has 4 valence electrons. And the reason that chemists care so much about valence electrons, to give them an actual name, is that those highest energy level electrons, or outermost energy level electrons, they're the ones that are actually going to participate in bonding. So those are the ones that we care about the most, because they make a really big difference. Okay, silicon still has 10 other electrons, or I'm sorry, am I looking at, 12 other electrons. But it's, those other 12 electrons are in the lower energy level, in energy level 2. So we're not as concerned about them because they're not going to participate in bonding like the 2 of the highest ones are. Okay, so, and it turns out that we can actually use the group number to tell us how many valence electrons we have only for our main group elements. So you could remember from, I think it was last week, the main group elements are the tall column elements, the elements that are in the taller columns on the periodic table. And there are a couple exceptions, of course, and we'll talk about those. But for the most part, the group number for those main group or tall columns on the periodic table, for those elements, I should say, tells you how many valence electrons you have. So number of valence electrons equals the group number for those main group elements. Okay? All right, so in order to kind of visualize that, let's actually go back up here to our periodic table. So as you're looking at for the group number, I would look at the top number, the 3A, 4A, 5A, 6A, rather than the other naming system or numbering system, because it's just so much easier. You can still figure out the valence electrons from the other numbering system, but it's a lot easier to use this top one. So I would use that rather than, sorry, I should point to it, this one below, okay? So just get in the habit of using that 8A, the AB system. It'll make your life easier. Okay, so if you're in group 3, right here, so that's these elements here, how many valence electrons do you have? Yeah, 3, because the number of valence electrons equals the group number for main group elements. What are the main group elements? Those are the tall columns. Okay. Okay, what about when you're in 5A? Yeah, 5 valence electrons. So nitrogen has 5 valence electrons, phosphorus does, arsenic does. So, and so on. And what about if you're in group 7A? Yeah, 7 valence electrons for every one of those elements that are in that group. Like I said, there are some exceptions, so let's talk about those. So looking at hydrogen and helium, specifically at helium for a second, helium has how many total electrons? Yeah, it has 2 total electrons, right? And I guess that's hard to see here because they don't actually have the atomic number, but helium's atomic number, whoa, that's really thick, is 2, okay? And the hydrogen's is 1. So if helium's atomic number is 2, we know we have 2 electrons. And since we don't even get to 8, helium doesn't follow that rule. of the group number equaling the number of valence electrons. We don't even have enough for that to happen. So that one's an exception, okay? So I'll draw a little star there. Hydrogen's a little bit easier because it is in group 1A, so it does have one valence electron, but it's kind of weird to say that it's a valence electron because it only has one electron total. So yeah, it's in the highest energy level because there's only one energy level for hydrogen. But yeah, so kind of an exception, kind of not, I don't know. But sometimes it trips people up, so that's why I wanted to mention it. Okay? All right, so here, this is just a table showing some valence electron configurations. So looking just at, I'm just going to show you kind of this one here. In group 8A, we just talked about that. Remember, helium's an exception because it only has 2, so it's kind of, that one doesn't really follow the rule. It doesn't have enough electrons, but that's okay because the other ones do. So let me get back to blue here. So notice that we have in our highest energy level for neon, because neon's in period 2, is it in period 2? Yeah, I was looking at the wrong element. Because neon's in period 2, that's the highest energy level, and it has 6 electrons in the p block and 2 electrons in the s block for a total of how many? Yeah, 8 total. Yeah. So it has 8 total in that highest energy level. So sometimes, if you're anything like me, you might only focus on this last one and you'd be like, wait a second, this doesn't follow the rule. It's only got 6. You have to count everything that has the energy level 2 because that's the highest energy level. So you got to count both your S's and your P's, okay? Same thing down here. We've got 3 is our highest energy level for argon. Okay, because why? Because it's in group 3. I'm sorry, period 3. And it has how many electrons? Yeah, 6. No, 8. Oh my gosh. Sorry, you guys. I think I need more coffee. It has 8 total electrons, valence electrons. Okay, same thing with krypton. Its highest energy level is 4. It's got 2 valence electrons in the S sublevel and 6 in the P sublevel for a total of 8. Gosh, I can't speak today. Okay, so I hope that makes sense. So let's keep moving along. I'm not going to do this learning check with you, but I will pause the, I want you to do it. So you're going to pause the video and try this out on your own. Okay, and just to keep the video quick, I'm just going to show you the solution. And then if you have any questions, you can ask me in person, okay? Or email me. Okay, so here's the solution. Let me know if you have questions. Okay, Lewis symbols. So Lewis symbols are cool. What Lewis symbols do is they represent the valence electrons as dots placed around the sides of the symbol for an element. So if your element that you're thinking about is magnesium, or that you're trying to represent, here's our symbol. And then around that symbol, we're going to place our valence electrons as dots. Why do I only have 2 dots for magnesium? Yeah, because magnesium's in group 2A, so it has 2 valence electrons. So let's just write magnesium group 2A, which means 2 valence electrons. Okay, so you can represent them in any of these ways. Some professors are picky and they want you to represent them in certain ways. I don't care where you draw those 2 dots, as long as you don't draw them right next to each other. So big no, don't do this. Don't do this. Don't draw the 2 electrons like that, okay? Why don't we want to draw the 2 electrons like that? Yeah, because electrons repel each other. So they don't want to be close together. They're not going to pair up like that if they don't have to. So eventually, if you have lots of electrons in your, or lots of valence electrons, you will pair them up, but only if there's no other option, okay? So at first, it's just like the bus example. They're not going to sit next to some stranger on the bus if they don't have to, okay? So, so you can draw it like this, you can draw it like this, you can draw it like this. I'm not picky about it. Technically, this is really the best of all of these because they're the furthest apart. But you can do any of these is fine, because I'll know what you mean. If you do put one next to the other one, I would mark you off for that, okay? Or mark you down for that. Okay, this is just showing some of the Lewis symbols for different elements in periods 1 to 4. You can see as you go to the right on the periodic table, the number of valence electrons is increasing. And why is that? Well, that's because our group number is getting higher and higher as we go to the right. So kind of makes sense, right? So you can look at that on your own time as well if you want to look at that more. Okay, so atomic size. It turns out that the size of these atoms are determined by the atom's atomic radius, which is the distance between the nucleus and the outermost electrons. And the reason for this is that there's an overall positive charge in the nucleus, right? The nucleus has protons and neutrons. And since those protons are positive and those neutrons don't have a charge, we have an overall net positive charge in the nucleus of our atom. And then our outermost electrons have a negative charge. So those electrons are attracted, both of them, the proton and neutron, are attracted to each other. So they're going to pull towards each other. And that's going to, dictate the atomic radius. Decide the atomic radius. Determine. It's literally right here. Determine. Determine the size of the atomic radius. Okay, so we've also noticed that atomic size increases for representative elements, main group elements, tall column elements, whatever you want to call them, from top to bottom of the periodic table, and then decreases within a period as a result of increased number of protons in the nucleus. So let's focus just on this second bullet point here. So increases for main group elements from top to bottom of the periodic table. So as we're going this way on the periodic table, as we're going down, our atomic size is getting bigger. And you can see that here. We've represented it here on this periodic table. That atomic size is getting bigger and bigger. Okay, so as you go up and down, as you go down the periodic table, you're getting larger in atomic size. Okay, and then let's look at this third bullet point. So we've also noticed that atomic size decreases within a period. And the reason for that is that there are more protons in the nucleus. So more protons in the nucleus, you have an overall positive charge in the nucleus. And the number of protons, well, I don't want to get into the specifics of it. Yeah, we'll save that for Gen Chem. But for now, just know that as you go, let me show you on the periodic table. As you go right on the periodic table, your atomic size is decreasing. Okay? All right. Let's keep moving along here. Sorry, I just don't want to get too in the weeds in this specific class. Save that for Gen Chem. Okay, so for representative elements, the atomic size increases going down a group, but decreases going from left to right across a period. Okay, and when I get my periodic tables for exams, I literally just draw these lines immediately. Okay, and I write atomic size or whatever. Just because there are several trends we're going to go over, and they sometimes are conflicting with the way the arrows are going to be written. Okay, so, wait, we looked at this. Didn't we look at this? Yeah, we did. I wonder why those copied like that. Okay, well, we haven't looked at these yet, so let's look at these. So ionization energy. So another trend that you'll notice in the periodic table is something called ionization energy. So in an atom, the electrons that are negatively charged, they're attracted to the positive charge of the protons in the nucleus. So there's we actually, in order to remove an electron from an atom, you need to put in a certain amount of energy. And that's what ionization energy is. It's the energy that's required to remove one of the outermost electrons, one of the valence electrons. Okay? So when an electron is removed from a neutral atom, we actually create a positive charge. So looking, and this is kind of weird, but it's a good segue into our next section. So here's our neutral sodium in the gaseous state, right? That's what that G means. We're adding energy, okay? And that energy is called ionization energy, and we'll talk about what that is in a little bit. And what we're getting out is actually sodium. It's still sodium, but it's sodium with a positive charge. Why? Because we've ripped an electron away from it. We've taken that negative charge. So what was before a neutral atom, when we had the same number of protons and electrons, is now a charged atom, because we've taken away one of the charges. So what do we have overall? Well, now we have a net positive on that atom because we took away an electron, which has a negative charge. And we call the energy required to do that, to take that electron, we call that ionization energy. Okay? So is there a... Yeah, there's a graphic down here. I guess we should read these other bullet points first. So as the distance from the nucleus to the valence electrons increases, we find that the ionization energy, the amount of energy needed to remove an electron from the outermost shell, decreases. So let's read that again. As the distance from the nucleus to the valence electrons increases, so distance from the nucleus to the outermost electrons, as that distance gets larger and larger, the amount of ionization energy required to rip that electron away is lower. So the ionization energy is low for metals and high for nonmetals. Okay. Where are the metals on the periodic table? I'll let you answer that question for yourself. And where are nonmetals? So that is where we get this trend from. We can see as we move to the right on the periodic table towards the nonmetals, the amount of ionization energy needed to remove an electron increases. Okay? And as we go down on the periodic table, the amount of energy needed decreases. Okay, so another trend. So with these trends, you guys, you got to just kind of, you need to like understand the concept behind it. But once you do that, I would just immediately write down the trends on a periodic table right when I get it for an exam. And that way it's just, you can't confuse yourself. It's right on your periodic table, right? Okay. Oh, and I guess we should talk about why. So I guess we should do that. So for a lithium atom, notice that the distance between the nucleus in a smaller atom like lithium, right, is pretty small. So the distance between the nucleus and that outermost electron, that valence electron, is small. Okay, so that attraction between the positive charge in the nucleus and the negative electron is really strong because they're close together. Okay, so it's going to take energy to rip them apart. As they get further apart and that distance increases, it gets easier and easier to rip that electron away. Why? Yeah, because they're further apart. It's easier, that force of attraction is lower as we have a higher distance between the nucleus and the valence electron. Okay, so easier to rip it away, and your ionization energy, the amount of energy needed to take that electron, decreases. Okay, the last trend, I think it's the last one. Yeah, the last trend we're going to talk about is metallic character. So an element with metallic character is one that loses valence electrons easily. So metallic character is more prevalent in metals, which is where we get the term metallic character, on the left side of the periodic table. And it's less for nonmetals on the right side of the periodic table, okay? Because those nonmetals do not lose electrons as easily. And that's why we think, so think about the noble gases. The noble gases have a, actually, I don't want to get into that yet either. Sorry. I'm getting ahead of myself because I get so excited. Okay. So for now, let me just read this last one. So metallic character increases going down a group as electrons are farther away from the nucleus. So let's read that again. Metallic character increases going down a group as electrons are farther away from the nucleus. So here's another little graphic to show you. So going towards the right on the periodic table, metallic character is decreasing. And going down, metallic character is increasing. Okay, and this is just something that we notice in nature. Okay, so again, I would urge you for these trends to write them on your periodic table and try to like memorize them. You do want to make sense of them, but it's going to help to memorize them as well, just so you don't start confusing yourself when you, because sometimes it can be confusing when you're writing a bunch of different arrows. So the more you know it, the better it is. Okay, I'll see you in the next video, and we'll talk about ions.